In this video, we're going to talk about one of Archimedes' proudest achievements, which was to show that if you take a sphere and you circumscribe a cylinder around it, then the sphere and the cylinder have volumes in a ratio of 2 to 3. And also, their surface areas are in the same ratio. Archimedes actually requested that a sphere and cylinder be put on his tombstone because he was so proud of this achievement. So today we're going to see roughly how the argument for this went. The key idea here is something called the Cavalieri principle, which is named after a mathematician who lived a few thousand years after Archimedes, but nonetheless Archimedes and other ancient Greek mathematicians used this quite often to compute volumes. The idea is that if you have two solids, so for example a cylinder like this and some weird shape like this, and if at every height the surface areas are equal, then the volumes are equal. So in terms of calculus, which is the language we would use nowadays, we would say that you're essentially integrating the cross-sectional areas to get the volume. And even though the Greeks didn't have calculus, they did have many of the ideas that later became the foundations of calculus, including this idea of splitting up volumes into very thin slices and then relating that to cross-sectional areas. Okay, so first we'll show that the sphere has 2/3 the volume of the cylinder surrounding it. But before we do that, we first need to know how to find the volume of a cone. Now, the volume of a cylinder is quite easy because it's just base times height. But the volume of a cone is 1/3 base times height, and again, this is something that's easy with calculus, but how did the Greeks find this? Well, essentially they did use calculus. So what they did is split this up into pieces that they knew how to find the volumes of, and then use that to approximate it. So something like splitting it up into a bunch of smaller slices until you get something that's a good approximation, and then in the limit you get an equality rather than just an approximation. So here's how that might have gone. So if you have a pyramid with a base that can be any convex polygon, the volume is always 1/3 base times height. And it doesn't depend on the shape of the base, only the area of the base. One way to see that is to start with, say, a pyramid with a square base. If you know that the volume of that is 1/3 base times height, then you can approximate the volume on the left with many pyramids with square bases inside it. So something like, you have this one, and then next to it you have this one. Okay, so when you add up all these volumes, all you're really doing is adding up the areas of the bases. All the heights are the same, and you'll approximate the total volume in this way. Okay, so you just keep tiling the base like this. Okay, so whatever the shape of the base is, it doesn't really matter. All that matters is the area of the base. So in the case of a square pyramid, which is probably easiest, one way to get this volume formula is basically take a bunch of slices that are squares. So this is a side view. Then basically all you're really doing is adding up the first n squares, where n is the number of slices you have. And, well, if you do a little bit of algebra, you know that that's going to be roughly n cubed over 3. You can get an exact formula, but that's not too important. All that really matters is that it's roughly n cubed over 3. So as you take a limit, this approximation gets better and better, and so you end up with 1/3 base times height, where this 3 is where the 1/3 comes from. But of course, in modern day calculus terms, we would say that it comes from integrating x squared. Okay, so that shows that the volume of any pyramid or any cone is 1/3 base times height. Now, the really clever part is how Archimedes turned this into the volume of a sphere. So what Archimedes did was he took a hemisphere, and then he took slices parallel to the base. Okay, now if our slice is at height h, and say the radius is r, then the cross-section will look something like this. So this will be h, and then this length down here will be r, which is also the same as that hypotenuse of the right triangle. So this leg here will be square root r squared minus h squared from the Pythagorean theorem. So the area of that cross-section will be, well, it's a circle with radius root r squared minus h squared, so it's just pi times r squared minus h squared. Now Archimedes recognized this as the area of another kind of shape, which is two concentric circles. So if you have a circle of radius r, and you take out a circle of radius h from inside it, then the area is exactly pi times r squared minus h squared. So what this suggests is that we should build a shape where the cross-sections look like these rings, and what that gives you is, on the outside you have a cylinder of radius r, and on the inside you have a cone, so that the radius of the cross-section depends on the height. Okay, so if this radius is r, and this height is also r, okay, it's not to scale, then if we go up h units and take a cross-section, the radius of the inner ring will be exactly h. Okay, so when h is 0, the inner radius is 0, you have a complete circle. When h is r, you have a circle of radius r minus a circle of radius r, which is 0. So as you vary h, these rings get larger or smaller. So the hemisphere and the cylinder with the cone removed have the same cross-sectional areas, so their volumes are also equal. Okay, and that common volume is, well, if you look at the cylinder, it's base times height, which is pi r squared times the height, which is r. And then you subtract off 1/3 of that area to get rid of the cone. So you end up with 2 pi over 3 r cubed. So that's the volume of a hemisphere, and then the volume of a sphere is just twice that. And now this is automatically 2/3 the volume of the surrounding cylinder because we've compared a hemisphere to 2/3 the volume of the surrounding cylinder. Okay, now how do we get the same result for the areas? Well, you can actually use the volume trick and do a little bit more calculus. So we know that the volume of the sphere is always 2/3 the volume of the corresponding cylinder. So if you change the volumes just a little bit, the change in volumes is proportional to area. So if you change the volumes just a little bit, so you start here with your sphere and you increase the radius a little bit, it's a bit hard to draw, what you end up with is a hollow sphere where the thickness is the change in the radius, so I'll call that delta r. Now you have a hollow sphere where the thickness is delta r, so the volume is going to be roughly the surface area times that little thickness. And the same argument works for the cylinder as well. So you take a cylinder, increase the radius a little bit, okay, now you have a hollow cylinder with thickness delta r. And so again, the volume is roughly the surface area times the thickness. Okay, but we know that these two volumes are in a ratio of 2:3. And so if we change the radius by the same amount, that tells us that the areas are also in a ratio of 2:3. Now, one further interesting property of this is that if we take this sphere and the cylinder around it, now if we cut this horizontally, on the sphere you'll have some curved band, and on the cylinder you'll have some band that's the same height, but it won't be curved on the outside, it'll be completely vertical. Now it turns out that these two bands always have the same surface area. So not only are the total surface areas the same, but every single slice gives you two regions with the same surface area. And one implication of this is that if you take the Earth and you project all the points on the Earth to a cylindrical map, it will preserve surface areas. So, for example, here's a bad drawing of North America. Okay, you project that horizontally onto the cylinder. There will be some distortion, but it will preserve areas. And then you just unroll this cylinder and you get your map that preserves surface areas. Now there's no way to give a map of the world without any distortions because you're trying to flatten a curved surface, and the surface of a sphere cannot be flattened without some distortion, but the area will be preserved.